Both direct current and alternating current Hipot testing methods offer unique advantages and disadvantages. Considering direct current Hipot testing, some advantages include sensitivity to insulation defects, especially those caused by moisture and contamination, and the ability to identify weak spots in insulation. Additionally, direct current Hipot testing equipment is generally less expensive. However, direct current Hipot testing also has drawbacks. It can stress dielectrics differently than alternating current, potentially leading to insulation breakdown. It can also cause electrolysis in dielectric materials and typically requires longer test times. Conversely, alternating current Hipot testing presents a different set of characteristics. Advantages of alternating current Hipot testing include a more representative simulation of actual operating conditions, as most high-voltage systems use alternating current power, a lower likelihood of damaging dielectrics over time, and shorter test times. The disadvantages of alternating current Hipot testing are that it is less sensitive to moisture and contamination and may not detect all insulation defects. Low-frequency alternating current Hipot testing, typically ranging from 0.1 Hz to 10 Hz, is a variation of alternating current Hipot testing designed to mitigate the disadvantages of direct current testing while retaining the benefits of alternating current testing. A key advantage of low-frequency alternating current testing is reduced dielectric stress. The lower frequency reduces the peak voltage applied to the insulation, minimizing stress and potential damage. Another advantage is improved sensitivity, as the lower frequency allows for slower charge accumulation in the insulation, which increases sensitivity to defects. Furthermore, compared to direct current testing, low-frequency alternating current testing can be completed in shorter time frames. However, low-frequency alternating current testing also has some disadvantages. It is typically more expensive, as low-frequency alternating current Hipot testers are generally more costly than standard alternating current or direct current testers. Availability can also be limited, as low-frequency alternating current Hipot testers may not be readily available in all markets. Another potential issue is resonance. The lower frequency can introduce resonance into the test circuit, which can affect the accuracy of the test. To summarize, while alternating current Hipot testing has become more prevalent because of its reduced risk of dielectric damage over time, direct current Hipot testing remains a valuable method for identifying insulation defects, especially where moisture and contamination are concerns. Low-frequency alternating current testing offers a compromise between direct current and alternating current testing, providing improved sensitivity and reduced dielectric stress. The appropriate choice between these three methods depends on the specific application and the specific test requirements. Let's delve deeper into the technical aspects of each testing method. Firstly, consider direct current Hipot testing. This method involves applying a direct current voltage to the insulation of a cable or component and measuring the leakage current. The applied voltage is typically several times higher than the normal operating voltage. The goal is to assess the insulation's ability to withstand high voltage stress without breaking down. The leakage current provides an indication of the insulation's condition. A high leakage current suggests insulation degradation or the presence of defects. One of the key advantages of direct current testing is its ability to detect localized weaknesses in the insulation. For instance, if there is a void or a contaminant within the insulation, it will create a localized area of high electric field stress. This high stress can lead to increased leakage current, which direct current testing can effectively detect. However, direct current testing has limitations. One significant limitation is that it stresses the insulation differently compared to alternating current. In an alternating current system, the voltage polarity reverses continuously, creating a capacitive charging and discharging effect within the insulation. This effect is not replicated in direct current testing, which can lead to misleading results. Another issue with direct current testing is the potential for polarization effects. When a direct current voltage is applied to the insulation, the dielectric material can become polarized. This polarization can mask certain defects or create artificial indications of insulation weakness. Moreover, direct current testing can be destructive to certain types of insulation. The continuous application of direct current voltage can lead to electrochemical degradation of the dielectric material, reducing its long-term performance. Next, let's discuss alternating current Hipot testing. This method involves applying an alternating current voltage to the insulation and measuring the resulting current. The frequency of the alternating current voltage is typically 50 Hz or 60 Hz, which is the standard power frequency in most regions. Alternating current testing is considered more representative of real-world operating conditions because most electrical systems operate on alternating current. One of the main advantages of alternating current testing is that it accurately simulates the voltage stress experienced by insulation in service. The continuous reversal of voltage polarity creates a capacitive charging and discharging effect, which is similar to what happens in an alternating current system. This allows for a more realistic assessment of the insulation's ability to withstand voltage stress. Alternating current testing is also less likely to cause destructive effects on the insulation. The alternating nature of the voltage minimizes the risk of electrochemical degradation. Additionally, alternating current testing can detect a wider range of insulation defects compared to direct current testing. For example, alternating current testing is particularly effective at detecting surface contamination and cracking, which are common causes of insulation failure in alternating current systems. However, alternating current testing also has some limitations. One limitation is that it can be less sensitive to localized weaknesses in the insulation compared to direct current testing. The capacitive charging and discharging effect can mask small defects or voids. Another limitation is that alternating current testing equipment is generally more expensive than direct current testing equipment. Now let's consider low-frequency alternating current Hipot testing. This method is a compromise between direct current and alternating current testing. It involves applying an alternating current voltage at a frequency significantly lower than the standard power frequency, typically between 0.1 Hz and 10 Hz. Low-frequency alternating current testing aims to combine the benefits of both direct current and alternating current testing while minimizing their drawbacks. One of the main advantages of low-frequency alternating current testing is that it reduces the stress on the insulation compared to standard alternating current testing. The lower frequency reduces the rate of voltage change, which minimizes the capacitive charging and discharging effect. This reduces the risk of insulation damage, particularly in aged or deteriorated insulation. Low-frequency alternating current testing also provides improved sensitivity to insulation defects compared to standard alternating current testing. The slower voltage change allows for a more accurate measurement of the leakage current, which can reveal subtle weaknesses in the insulation. Furthermore, low-frequency alternating current testing can be performed on long cables without significant capacitive loading effect. The lower frequency reduces the capacitive reactance of the cable, which minimizes the current required to charge the cable. This makes low-frequency alternating current testing suitable for testing long runs of underground cables. However, low-frequency alternating current testing also has some disadvantages. One disadvantage is that it requires specialized testing equipment, which can be expensive. The equipment must be capable of generating and measuring low-frequency alternating current voltages with high accuracy. Another disadvantage is that low-frequency alternating current testing can be time-consuming. The lower frequency means that it takes longer to complete a test cycle, which can increase the overall testing time. In addition to these technical aspects, it is important to consider the relevant industry standards and guidelines for Hipot testing. Standards such as Institute of Electrical and Electronics Engineers 400.4 and International Electrotechnical Commission 60,502 provide detailed recommendations for performing Hipot tests on various types of cables and equipment. These standards specify the test voltages, test durations, and acceptance criteria that should be used for each type of test. It is essential to follow these standards to ensure that the Hipot tests are performed safely and effectively. Furthermore, it is important to have qualified personnel perform Hipot tests. Hipot testing involves high voltages and currents, which can be dangerous if not handled properly. Personnel performing Hipot tests should be properly trained in the use of the testing equipment and should be familiar with the relevant safety procedures. They should also be able to interpret the test results accurately and make informed decisions about the condition of the installation. In conclusion, the choice between direct current, alternating current, and low-frequency alternating current Hipot testing depends on a variety of factors, including the type of insulation being tested, the operating voltage of the system, the age and condition of the insulation, and the specific goals of the testing. Direct current testing is suitable for detecting localized weaknesses and is relatively inexpensive, but it can stress the insulation differently than alternating current and may not be appropriate for all types of insulation. Alternating current testing is more representative of real-world operating conditions and is less likely to damage the insulation, but it can be less sensitive to localized weaknesses. Low-frequency alternating current testing offers a compromise between direct current and alternating current testing, providing improved sensitivity and reduced stress on the insulation, but it requires specialized equipment and can be time-consuming. By carefully considering these factors and following relevant industry standards, it is possible to select the most appropriate Hipot testing method for a given application and ensure the safety and reliability of electrical systems. Understanding the dielectric properties of insulation materials is also crucial for effective Hipot testing. Dielectric materials are substances that are poor conductors of electricity but can support an electrostatic field. They are used in electrical cables and equipment to insulate conductors and prevent electrical breakdown. The dielectric strength of a material is its ability to withstand an electric field without failing. When a voltage is applied to a dielectric material, it becomes polarized. The molecules within the material align themselves with the electric field, creating a dipole moment. This polarization reduces the electric field within the material and increases its ability to withstand voltage stress. However, if the applied voltage exceeds the dielectric strength of the material, it will break down, resulting in an electrical arc or discharge. The dielectric strength of a material depends on several factors, including its composition, temperature, and frequency of the applied voltage. Some common dielectric materials used in electrical cables and equipment include polyethylene, cross-linked polyethylene, ethylene propylene rubber, and mineral oil. Each of these materials has its own unique dielectric properties and is suitable for different applications. For example, cross-linked polyethylene is commonly used in high-voltage cables because of its high dielectric strength and excellent resistance to heat and moisture. Mineral oil is used in transformers and other high-voltage equipment because of its high dielectric strength and ability to dissipate heat. When performing Hipot testing, it is important to consider the dielectric properties of the insulation material being tested. The test voltage should be selected based on the dielectric strength of the material and the operating voltage of the system. The test duration should be long enough to allow the insulation to become fully polarized, but not so long that it causes damage to the material. The leakage current should be monitored closely during the test to detect any signs of insulation breakdown. In addition to the dielectric properties of the insulation material, it is also important to consider the effects of temperature and humidity on Hipot testing. Temperature can affect the dielectric strength of a material, with higher temperatures generally leading to lower dielectric strength. Humidity can also affect the insulation resistance of a material, with higher humidity leading to lower insulation resistance. Therefore, it is important to control the temperature and humidity during Hipot testing to ensure accurate and reliable results. It is also important to consider the effects of aging and environmental factors on the insulation material. Over time, insulation materials can degrade due to exposure to heat, moisture, chemicals, and other environmental factors. This degradation can reduce the dielectric strength and insulation resistance of the material, making it more susceptible to failure. Therefore, it is important to perform regular Hipot testing to assess the condition of the insulation and detect any signs of degradation. In addition to performing Hipot testing, there are other methods that can be used to assess the condition of insulation materials. These methods include insulation resistance testing, dissipation factor testing, and partial discharge testing. Insulation resistance testing measures the resistance of the insulation material to the flow of direct current. This test can be used to detect moisture, contamination, and other defects in the insulation. Dissipation factor testing measures the energy loss in the insulation material due to polarization effects. This test can be used to detect degradation of the insulation material due to aging or exposure to environmental factors. Partial discharge testing detects the presence of small electrical discharges within the insulation material. These discharges can be a sign of insulation weakness and can eventually lead to insulation failure. By using a combination of these testing methods, it is possible to obtain a comprehensive assessment of the condition of insulation materials and ensure the safety and reliability of electrical systems. The frequency of Hipot testing should be determined based on the type of equipment, the operating conditions, and the recommendations of the equipment manufacturer. High voltage equipment that is critical to the operation of a facility should be tested more frequently than low voltage equipment. Equipment that is exposed to harsh environmental conditions such as high temperatures or humidity should also be tested more frequently. In general, Hipot testing should be performed at least every 3 to 5 years, or more frequently if recommended by the equipment manufacturer. In addition to routine Hipot testing, it is also important to perform Hipot testing after any maintenance or repairs are performed on electrical equipment. This ensures that the insulation has not been damaged during the maintenance or repair process. Hipot testing should also be performed after any significant event that could have stressed the insulation, such as a lightning strike or a power surge. By following these guidelines, it is possible to ensure that electrical equipment is properly insulated and protected from electrical breakdown, which can help to prevent accidents, injuries, and equipment damage.